Okay, so for this problem, we're going to find the total impedance flowing through the circuit, which means we're going to have to reduce all of these elements down to one element. We're finding the voltage drop across this R2, and we're going to find the current through this inductor of X of L2. In order to find the voltage drop across here, which we don't have, and across here, which we don't have, is we need to figure out the total impedance so we can figure out what the total current is and work our way back. Once we find the total voltage here, we have the answer for V2, and with that voltage divided by this impedance, we can get that total current. So those three things that their problem's asking for, we'll do the math on the big board, but I'll redraw the circuit here so you can see how it'll be redrawn. I'm not going to use impedances of Z sub 1, Z sub 2, Z sub 3 like some of my other problems did. I'm just going to leave it the same here, but I will put boxes for the elements so we can see how this progresses easier. So redraw, let's start with redraw number 1 right here, and I'm going to do 2 steps here. I'm going to just put E here, I'm going to put a box here, say R1, then here we're going to go up, and then here we're going to go down. So here we have X of C, here we have X of L1. And you notice these two are in parallel, these two in parallel, all three of them are in parallel. There is a fancy way to go about doing this when they're all together, and that is you do the product over sum of all three plus the sum of all of them together in the denominator. However, I'm going to save that for its own video. I'm going to do this step by step so we can see how it can be done with the same approach every time, because we know that two things in parallel are product over sum, and we can do the same thing with these two, and we will. But right here, we'll put a box there, put a box there, and one here. We're all going to come up to this point. But this is not the ground, this is all the way over here. Here's our ground. This is R2. This is V2. Let's see. R3. X of L2. This is I sub L. I'll put the Z sub T here. So notice, I didn't do 2 steps, I just redrew it. But notice that I just changed the boxes. It's a lot easier to see how they can be condensed. I'm going to go ahead and do this one first. So let's see, Z sub 1 is going to be equal to X of C in parallel with X of L1. X of C in parallel with X of L1, which is equal to X of C times X of L1 divided by X of C plus X of L1. So we got Z sub 1. Okay, I'm going to redraw the circuit right up here in a smaller fashion so we can get everything on the board. This is our Z sub 1 right here. This is our R1. And then here, really small. Okay, see, we have R2 here, R3 here, and then X of L2. We're still finding this total impedance, and we're still finding the voltage drop across here, V2. we're also finding the current through this I sub L. Oh, and don't forget the ground. Alright, so now we get this. Let's do this. Let's do it one at a time. Let's do R2 and parallel with R3. That way we end up with a total impedance of 0. So let's say Z sub E is equal to R2 parallel with R3, which is equal to R2 times R3. So when I redraw the circuit, we end up with E here, this is positive, negative. Okay, positive, negative. And then here we have R1, Z sub 1, series with R1, and then Z sub B. But then here we also have X sub L2. That is the correct drawing right there. So this is the almost the finalization. Z sub, let's say Z sub 3C is these two in parallel. Okay. Z sub C is equal to Z sub B parallel with X sub L2, which is equal to Z sub B times X sub L2 divided by Z sub B plus X sub L2. Well, if that becomes one element, we know what our total impedance is. And here, we'll redraw it right here. E, we have R1. Here we have Z sub 1. And then here, we can just bring this down to this point and say Z sub C. Alright, so see, we got the total impedance. Z sub T is equal to R1 plus Z sub 1 plus Z sub C. And to make this a little more consistent, let's make the Z sub 1 a Z sub A. Z sub 1, Z sub A. Now, because we got Z sub A, Z sub B, and Z sub C. I went from Z sub 1 to Z sub B. Let's just keep it consistent. But this is the algebra behind this circuit problem where you're just finding a total impedance. Now, I haven't gone backwards yet. Once I find this value, then I can find out what the total current is through that whole source, because we have the voltage drop. And I work that current back through here. Well, notice that the current, whatever that current is, let's say it's I, that current's going to be the same through here, whatever it is. Meaning it's going to be the same through Z sub 1, that's going to be the same through Z sub C. We know what our total impedance would be. That solves one of the problems. So we're going to find a V2, but that's over here with Z sub C. So we know what the current is to Z sub C. We find a voltage drop across V sub C. That voltage drop across here is the same for all three of these elements. So I take that voltage, that's equal to R2, the V2, and I take the voltage divided by the impedance, and I get that current. And we'll do that on the board. Impedances that we calculate to be, we got Z sub A, Z sub B, and Z sub C, and ZT for our total impedance. Z sub A is equal to X sub C and parallel to X of L1. Okay, well this is easy. This is X of C1 right here. We have 4K ohms at an angle of -90 degrees. Alright, so this is Z sub A times X of C1, X of C times X of L1. So this is 4 k ohms at an angle of 90 degrees times X of L1, which is 6 k ohms at an angle of 90 degrees. These are negative and positive 90. When we add them together, we get 0. Here, we're going to multiply these together, add these together, but we're not going to have any X value. We're just going to have a Y value here. So X of C plus X of L1 becomes J2. Okay. Now if we rewrite this down here, we know that 6 times 4 is 24. So we have 24, and then K times K, that's 1,000 times 1,000, so we get mega ohms squared. That's at an angle of 0 degrees. And we're going to divide that by 2 k ohms at an angle of 90 degrees. Now, I can do the math of this in my head. Mega ohms divided by K is K, and 24 divided by 2 is 12. So we get 12 k ohms at an angle. If we add 0 minus 90, we get negative 90 degrees. So this is acting as a capacitive load for Z sub A. Now Z sub B is R2 in parallel with R3. Oh, I didn't write R3, did I? Yeah, I did. I wrote it here. So R2 is in parallel with R3, but remember what I said about product over sum? If they're the same value, it's always half of what that resistance is. Now, I'll show it here, but our Z sub B is equal to R2 parallel with R3, which is equal to 6.8 k ohms at an angle of 0 degrees times 6.8 k ohms at an angle of 0 degrees. Now we're going to divide this by 6 plus 6 is 12, 8 plus 8 is 16, divided by 10 is 1.6, so 1.6 plus 12 is 13.6. And this is going to be k ohms at an angle of 0 degrees. What's 6.8 times 6.8? Well, I'm not going to do that in my head. 6.8 times 6.8 is 46.24. 46. I keep writing it wrong. So this is ohms squared, and this is divided by 13.6 k. Notice that the angle is always going to stay the same. It's always going to be 0 degrees. But what's 46.24 divided by 13.6? 3.4. So this is equal to 3.4 k ohms at an angle of 0 degrees. Notice it's half of the value of our R2 and R3. It would be different if they were different values. Because of the same value, we get half. So that's actually a quick way to get that value. We don't have to show the calculation here. But I do it because there's a lot of people that don't know how it's done. Z sub C is another parallel combination. Is Z sub B in parallel with X of L2. Now we know what to do here. Z sub B is simply this value at 0 degrees. And since we're going to add it to, we know what this value is in rectangular form and polar form. This is great. Right here, Z sub B is 3.4 k ohms at an angle of 0 degrees times X of L2, we have is 8 k ohms at an angle of 90 degrees. And we're going to divide that by the sum of these two. Well, this is going to be simply 3.4 plus J8 times k ohms. I'm going to bring our Z sub C up here. Z sub C, that's equal to 8 times 3.4. So 27.2. And we have mega ohms squared. And that's going to be an angle of 90 degrees. But then this will be different. We have the square root of 3,400 squared plus 8,000 squared. 8692. Let's just put the decimal values there. This is going to be ohms at an angle of inverse tangent of 8 divided by 3.4. So 66.97 degrees. All right, so to calculate Z sub C, we take this value divided by that value, and then 90 minus this, to 66.97. So the 27 now I'll divide that by 86. 92. Take that, divide by that. 3129. This is at an angle of, we get 23.03 degrees. If we find the rectangular form of this, we get 2880. And if we do the sine of that value, we get 1224. This is ohms. Okay, now we know what Z sub T is, because that's R1 plus Z sub A plus Z sub C. We know what the rectangular form is of Z sub C. We know what R1 is, and we know what the rectangular form of Z sub B is. Not Z sub B, Z sub A. So this is equal to 2K ohms plus a negative J, 12K ohms, and then we're going to add 2.88K ohms plus J of 1.224 K ohms. I could have brought all the K ohms out. I just want to show how they can all be distributed out of those parentheses. I'll rewrite it just so you can see what I'm talking about. 2 plus, let's say this 2 minus J12 plus 2.88 plus 1J 1.22. And we can put the K ohms out here on the end. This makes it a lot easier to look at when we're adding them together, because we get here 4.88 minus J12 plus J 1.22. Well, let's just do that in our calculator. It's 10.78. Negative J of 10.78. This is K ohms. Let's find the polar form of this. Square root of 4,880 squared plus 10,780 squared. We get 11,833 ohms. That's going to be an angle of, let's see, negative 10.78. Okay, negative 10.78 divided by 4.88. We get negative 65.44. 0.64, not 44, 64 degrees. So here's our total impedance right here. Here's the first answer to the problem. Okay. We use Ohm's law. I is equal to E divided by Z sub T, which is 120 volts at an angle 60 degrees. And that's divided by 11.8K ohms at an angle of negative 65.64 degrees. This value of current, which is going to help us get to V sub 2 and I sub L. So I sub L is right here, current flowing through L2. And the V2 is across R2. So we're looking across right here for V2. Now what's this current I? Well, that's going to be 120 divided by 11,833.1. We get 10.1 milliamps. And that's at an angle of 60 minus that value. It's actually plus, so 60 minus negative 65, 125.6 degrees. So this is, now we have the total current flowing through the circuit, which I'll redraw right here. Here's our E. Here's our Z sub T. Here's our ground. Current's going to flow in this direction, assuming they're going to flow in both directions as it's an AC signal. But assuming that the path that we're tracking on this circuit, we're going to go this way. So if this is our positive, this is our negative, then this is our positive, this is our negative. Here's our I flowing through the circuit, through this element, Z sub T. And what is Z sub T? Well, let's redraw the circuit again. We have R1. Then we have Z sub, was that right? Z sub 1, then Z sub C. Z sub A. That's what Z sub T is, Z sub A. And now that I look at it, one of the circuits I draw in my, I put Z sub 1. That's not Z sub 1, Z sub A. Notice here that they're all in series. This current's going to flow through all of these. But we don't need any voltage drops or really the current values or anything for R1 and Z sub A, because this value of impedance has the values that we are looking for in order to figure out what current or what voltage it's asking for. So here's our positive, here's our negative, positive, negative, positive, negative, positive, negative. All right, so I'm going to redraw this again and say I got our E, R1, Z sub A, and then Z sub C. Z sub C is ZB in parallel with X of L2. So we could say here, ZB, X of L2. And ZB is where our voltage V2 we're looking for is. And the current's flowing through this element L2, F of L2. Because ZB is a parallel combination of its own, but that has the voltage drop that we need here. So if we find the voltage across ZB, then we already have that answer. And since we have that voltage drop across ZB, it's the same voltage drop across X of L2, so we take the voltage divided by this impedance, we'll get the current flowing through that element. So that gives us the final answer. Then here we could write positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. All right. We know what the I is. Let's find what the VC is. VC is equal to I Z sub C, which is equal to 10.1 milliamps at an angle of 125.6 degrees. We multiply that by Z sub C, which is 3129 ohms. That's at an angle of 23.03 degrees. Now V sub C our V sub C is going to be 31.73 volts, and that's at an angle of these values added together, which is 148.6 degrees. So here's our answer. That's V sub C, which is equal to VB, which is equal to V2. This is our answer for the second. Okay, here's our first answer, Z sub T. Here's our second answer, V sub C. Probably write that right here. Z sub T. That way it's out on the open, it's all in the box, just like this one. But now we're going to find the current flowing through here. We know what that voltage is. We can take that voltage, divide it by X of L2, which is 8,000 ohms, and we get 3.97 milliamps. So this V sub C is equal to the voltage across X of L2, which is equal to, and so what we're really looking for is it IL. Okay, IL is equal to V X of L2 divided by X of L2. So we get 31.73 volts at an angle 148.6 degrees. And we're going to divide that by X of L2, which is 8,000 ohms at an angle of 90 degrees. And then this, IL, simply 3.97 milliamps. And that's at an angle of 148.6 minus 90. That's 58.6 degrees. And this should be the final answer for the current.